Hi everyone, welcome back to Perez on Technology Security. In today's module, we'll discuss two separate topics. The first one is threat modeling, where threat modeling we mean understanding system weaknesses, thinking like an attacker, trying to understand how a system could be attacked, all different possible attack vectors, and outline them, strategize, prioritize. So we'll see how we can think as an attacker in order to protect the system. And the second part is the discussion about assessment environments. So once we have the threat modeling in place and we can understand what attacks we need to protect against, we can develop a mechanism, a test bed, some kind of a system that replicates to an extent our target system in order to develop and test cybersecurity solutions. So let's dive in and start with threat modeling. In order to be able to enumerate the threats, and create a systematic approach to be able to identify most of them, if not all of them, we follow a process that we call threat modeling. The definition of threat modeling is the process of identifying potential threats from various perspectives, including the attacker, risk and software points of view, before they can become system threats. So in other words, we're trying to find a systematic way of enumerating all the possible threats. So in the example of the Marucci water attack we saw before, one threat could have been the communication failure, that someone can interfere among the middle attacks, as we saw in the attack that actually took place. Another possible threat could be malware in the PLC. For example, here in the PLC, you could have malware coming from a USB stick or some other kind of access to the system by an insider, either accidentally or maliciously, that leads to having persistence on behalf of the attacker and the ability to further exploit the system. So here I'm just saying a few things: communication failure, PLC, malware, but this is me brainstorming. Threat modeling involves a more systematic approach that you have to make sure you cover all the possible paths and you can cover all the possible approaches the attacker can have when they're targeting a system. Threat modeling is an essential component of an appropriate cybersecurity strategy. Threat modeling allows you to assess vulnerabilities and find weak points within the system. And it also allows to create an attack library listing the most possible attacks that would target the system, and that allows you to prioritize the security analysis and make sure you target what's the most important parts of the system and your security strategy. And once you do the threat modeling, you can deliver the concrete information to risk assessment, and then this can be followed by developing mitigating strategies. Looking at the graph on the right-hand side, the graph has two axes, likelihood and cost. And once you start your threat modeling, you find out that some threats are very likely to happen, some threats are less likely to happen, and mitigating against those threats may have high or lower cost. And here is where the prioritization starts. For example, a straightforward example would be that if something is very high likely to happen, but the cost of mitigating against is low, then it's definitely worth mitigating against that specific threat. On the other hand, if something it's most probably not going to happen, it's very difficult to happen, and there's a very high cost involved in protecting that, then maybe in your strategy you decide that you won't mitigate against, and you would accept the risk of this threat materializing. So threat modeling gives you the list and also the cost associated with mitigation against every possible threat, and then the risk assessment that follows will give you answers on what needs to be protected against and what not. What is the most tricky part is what if something is very likely to happen but it's very expensive to protect against. For example, here, this part of the graph, or on the other hand, the other extreme, something that's most probably not going to happen, but it's easy to protect against. Do you actually bother doing it or not? That's up. Again, all the answers are coming from the risk assessment that we'll see in the following lectures. So threat modeling has to some extent be realistic, and I'm going to allow a few seconds for you to read this existing comic. So the comic is taking a stab at proper threat modeling. So if you want, what this is trying to say, you're trying to protect your sensitive data, and to do it, you're trying to find the strongest encryption you can think of. That's a 4,000-bit RSA in this example. So someone is thinking, okay, to protect my data, I'm gonna encrypt it with a 4,000-bit RSA. So the threat in my mind is someone cryptanalyzing and reversing RSA in order to get access to my data. And this to happen, this is very difficult for someone to reverse RSA, especially with those bit sizes. It would take probably more than a lifetime of the universe to reverse with classical computers to reverse the password. But what is missing in the thought process, or well, in the threat modeling, is that there's a second way to access the data, to decrypt the data, and that is getting access to the password. And to get access to the password, since the human knows the password, you can go to the human and use some way like blackmail, threaten, intimidate, bribe in order to get access to the password. So this comic here is trying to give an idea about threat modeling. We shouldn't think about the obvious thing, but there could be other ways that other weak points in the system we need to protect against. So in this module, we'll see threat modeling frameworks that give us a more systematic approach to address threat modeling, and have two separate categories. One is generic IT ones that they're very useful to know in order to provide some guidelines in our way of thinking. And then we'll also see a more ICS specific one developed by Mitre called the Attack ICS framework. There's some other approaches like the IEC 62443 that we'll discuss when at the point of the class we'll be discussing standards. So let's start with the threat models, the threat modeling frameworks, starting with STRIDE. So STRIDE is an acronym and it classifies threats based on their effect. So every threat modeling approach is taking a different way of approaching the threat modeling problem, and STRIDE is classifying threats based on effects. So you're thinking of effects first, and per effect, you try to think of the possible threats that can cause the effect. Quickly going through the effects, the first one is spoofing, is where a person or a program successfully identifies as another by falsifying data. So you may be doing admin impersonation, or you change the data as they move around the network, and that gives you some kind of legitimate advantage. The T stands for tampering. So tampering is sabotaging. It's used to intentionally modifying something that can cause some harm further down the chain. R stands for repudiation. So remember, from computer security, information security, no repudiation means a service provides proof of the integrity and origin of data, or authentication that what you got is genuine with high confidence. I is for information disclosure. So this is unwanted dissemination of data, technology, or privacy. D stands for denial of service. This is when the system stops responding, a machine or a resource becomes unavailable temporarily or indefinitely, and that disrupts service of a host. And then finally, E stands for elevation of privilege, and this is when, by exploiting a bug or a vulnerability, you manage to get escalated privileges in the system. If it's a PC, you go from user to kernel or root mode. If it's a regular PLC, you may have some admin access that allows you to do more advanced things, such as changing set points or other effects. So here, STRIDE, it allows you to enumerate threats by effect. So you think, okay, what can cause elevation of privileges? This attack. What can cause spoofing? This attack. And to give some examples and tie them to what we've seen so far with the real attacks, Stuxnet, for example, did some data tampering, because when the data was going back to the operator, it was falsified, and the operator could see that nothing was wrong in the actual process. Havex, if you remember, it was a malware that had knowledge of industrial protocols, and it was doing mostly reconnaissance. So in a way, it was information disclosure. Triton was more on the, it did many things. It changed the firmware, so in a way it was also tampering. And this tampering allowed magical packets to be identified as special packets, and then the attacker could send their own payloads to the system. And finally, Ukraine Power Grid we can think of denial of service, because denial of service, remember when the operators try to use the VPN to connect back and try to defend against the attack, the firmware was corrupted, so they couldn't connect. So here, the slide, I fill in some of, again, you think of the effect. When in the slide firmware, you think of the effect first, like admin impersonation for spoofing, tampering, you can corrupt firmware, you can change the firewall, or you can inject code. Repudiation, you tamper with the system time or age critical events. Information disclosure, eavesdropping on buses, Habeck attack, man-in-the-middle attacks. Denial of service, firmware corruption or corruption of certificate, and elevation of privilege. An example here is unauthorized access. We now move to DREAD. That is again another acronym for how it approaches the threat modeling. So threat modeling here, instead of going by effect, we're trying to understand every threat by severity. So how important is every threat? And in a way, the two frameworks are complementary. So STRIDE goes by effect, DREAD goes by importance. So in a way, you can combine them and have the enumeration of the effects, and then you can give a number to every threat. So here, the DREAD stand for damage, reproducibility, exploitability, affected users, and discoverability. So for each one of these properties, you take every threat. Let's see an example of the radio frequency attack on the SCADA system, the Maruzzi attack we talked before. And the damage of the system was high. So since we do a qualitative low, medium, high, this would be high damage here. Reproducibility was low because you have to have very detailed knowledge about the system. So very specific individuals would have been able to manage the attack. So you can think of it, this is low. Exploitability, how much effort it takes to be exploited. So you assign a number based on your estimation, and you move down the list to provide the numbers, and you can sum up the numbers to come up with a risk rating. So this allows you to prioritize. If you put all your possible threats and they have a number attached to it, you can start by the higher number and try to address those given your budget, given your constraints, and given what you want to prioritize. So I mentioned you can combine the two. DREAD and STRIDE can be used together for comprehensive cybersecurity assessment. Here you start with STRIDE and you go by effect. So I put some possible threats here, and I classify them by the different effects they had. And then for each one of them, you can assign a different number, low, medium, high, to the DREAD assessment. So as an example, if we do in the Ukraine power attack, the serial to Ethernet, the modem firmware corruption. So here it's a DOS attack, since the operators did not have access to the substation to be able to defend against the attack. It's a DOS attack, denial of service, and we can start filling in the table. So damage was high, the reproducibility was low, it's difficult to reproduce the attack. Exploitability is there, same with the number of affected users, and discoverability can also be thought as low. Again, there's no perfect way of right answer for everything, right? 1, 2, 3. You make an assessment based on what you think. But if you're consistent in your analysis, the point of combining the frameworks is, again, to have a prioritized list to make sure you address what's most important about your system. A third framework I'd like us to take a quick look at is called PASTA. PASTA stands for Process for Attack Simulation and Threat Analysis. And it's different from the others because it focuses on risk. So it's a more risk-centric methodology. And it starts by making sure that business objectives align with technical requirements, and also takes into account compliance and business analysis. So very quickly, what PASTA does, it has 7 steps that we start by defining objectives. What are we trying to do with the threat modeling? And then the technical scope, what are the boundaries of the technical environment, and what do we have in it, right? What is the infrastructure, application, and software dependencies in the system? We'll move on to the composition of the application, use cases, actors, assets, services. So we're trying to create some kind of a data flow and find the trust boundaries, what do we trust more, less, nation states, cyber criminals, insider attacks. And then we move to threat analysis that will go to attack scenarios and do some regression analysis, security events, and threat intelligence correlation and analytics. Then, vulnerability and weakness analysis, we try to see what vulnerabilities are applicable to our system by seeing the scoring mechanism, CVSS, CWE, finding use cases, vulnerability mapping with threat trees, or in the attack modeling phase, we can do attack trees. We'll see an example later that we try again. Now, we're at the point when, after we create objective, what are the possible actors that can deliver the attacks? Now we're doing the attacks, and at the end, we're doing the risk and impact analysis that we're trying to understand how to implement countermeasures, how to implement defenses, and what is the strategy we need to follow. So PASTA framework is more risk-centric to an extent. So at some point in the PASTA threat framework, but we saw that before, there's some kind of attack modeling. So it's very important to be able to, once you have a threat, once you have a threat, to be able to map it to possible attack scenarios that can make the threat possible. One of these ways is called an attack tree, and you may have seen that again in information and computer security. So attack trees are more a formal, methodical way of describing security of systems. So in a way, it's a tree. So you can think of it as there's a root node, and then there are branches that have leaves, and then you have different levels. So in this example, your threat, the final goal of the attacker is to open a safe. We're talking about a house that has a safe, and we're trying to open the safe. So you try to start enumerating the possible ways you can open the safe. You can pick the lock, or you can break, you can cut it open, or when you install it, you do a supply chain attack. So you attack the installation process to make sure it's installed improperly, so you can later access it. Or you can learn the combination and use it to enter the safe. And learning the combination also has its own tree underneath. You can learn it by finding it somewhere, or you can try to get it from the target. And finding may be difficult, getting it from the target may be easier. You can get it also in various ways. You can threaten the individual who knows the combination. You can blackmail them. You can eavesdrop, so you can hear the person saying it, or you can bribe the person to give you the combination. An eavesdrop can also be split into, you listen to the conversation, and you also make sure you get the target to state the combo. And there are also primitive Boolean operators here. So if you have straight lines and OR conditions, so to open the safe, you need to do one of the four. But here, to eavesdrop, you need both to listen to the conversation and then get the target to say the combination. So the attack tree, again, it enumerates all possible ways, and then you can use that as in part of your threat model. You can assign impossible or possible values. May be impossible to pick it. It could be more possible to cut it open. And this gives you some priority on what is more highly likelihood, so you can focus more your resources on protecting against those. So in order to show attack tree development in the context of operation technology, let's go back to the Ukraine power grid attack, and let's talk about the final goal of the adversary, that was a substation compromise. So to compromise the substation, I can think of two possible ways. One, to do it remotely, and one to do it physically. So remotely means you do it from the internet somehow, you don't go to the substation. Well, physical means you go to the substation, right? And they're both possible threats, and it really depends on the adversary's capabilities, and also on the utility side, on how much security they have in their premises, to understand what is the best way for the attacker to compromise the substations. So let's focus on the remote part. What are the possible ways you can have remote access to a substation? Let's think a bit. What actually happened is, if you remember from the historical incidents, the attacker stole the VPN credentials that allow remote access. So one way of accessing remotely is to steal the VPN credentials. But there are other ways. You can do secondary system access. If you remember the target attack, the attackers targeted the HVAC system and then they enter the main system. So you can find maybe another way to attack, to get access to the substation control, maybe attacking the secondary system. Or there could be the possibility that the vendors have access to the substation for various reasons, including maintaining and upgrading the devices, or some other way you can do more a supply chain attack. So you can attack the vendor, or maybe you can attack the vendor's website and you put a malicious firmware on the vendor's website, and once the operator is downloading the malicious firmware, then you have access to the system. And you can further break down these attacks. The VPN access happens through spear phishing in reality, but you can have other ways to steal the credentials, or to get the credentials. Spear phishing is one, but again, anything like bribe, blackmailing, anything that has to do with social engineering is possible to be able to get VPN access, to get remote access, to compromise the substation. On the physical access side, you have to find some way to physically enter the premises, and we can think of a few. You can break the lock at night when nobody's there and go through. May be difficult if there are fences, if there are security cameras, if there are security guards. It may be difficult to do, but maybe the substation is far away, is unmanned, and it may have a camera that you can easily disable. Or you can manipulate an insider, again, so you can bribe or threaten them to give you physical access to enter the substation, or you may impersonate, you steal someone's ID card, like access card, or you fake you're them, and then you enter the premises to do an attack physically now to be able to compromise the substation. So this is a very simple attack tree that maps into a real attack we've seen that compromised several substations in Ukraine's power grid.